So today we're going to have a look at some practical reasons why we would want to consider or want to find whether a point is a maximum or a minimum. So we learned about stationary points, and then we learned how to use the second derivative in order to calculate if that stationary point is a minimum, a maximum, or possibly even a point of inflection. So generally what's going to happen is we're going to be given some scenario, and we're going to have to make an equation relating the variables of the scenario, and then we're going to have to differentiate in order to find the stationary points, and then use the second derivative to calculate whether that stationary point is a minimum or maximum. So in this example here, we have a flat sheet of metal, and what we're considering is we'd like to change this into a box, right? And this box will then have some volume. And we can vary the shape of this box by changing how much of the cutout we have. So we can use X as the amount that we're taking away from the corners before we fold it up. So we'd be taking away a piece and then folding obviously along these lines, lifting the box up, and it would then introduce some volume. So logically we can work out if X was 0, we would have no volume because this sheet would just be completely flat. It would have no height. All right, and if it had no height, it would be multiplying by 0, and therefore the volume would be 0. Now you can imagine as we change the value of X, the cutout is getting bigger and bigger, and so the sides of the box are getting deeper and deeper. But every time we change X, we're also making the dimensions of the length and the breadth, we're making them smaller. So even though we're making the height bigger, we're making the internal dimensions smaller. And so by varying these amounts, we could get to an optimal amount where we would get the most volume, right? And so if we could find some equation to relate these variables, we could differentiate them, right? And I'm going to show you in a few minutes what the equation would look like, and you can see how the volume would change in a graph as we change the value for X. So our first job is going to be to show that the volume is equal to this equation. So the best thing to do is write down the equation for the volume of a cuboid. So the volume is going to be equal to length times width times height. So let's look at the length. The length, we have a total of 24 centimeters, and the length of the box will depend on the value of X. Okay, so I have the same bit being taken away off both sides. So the length that I'm interested in will be this piece here, and that length will be the length, the total length minus 2 times X. And then the width will be the same idea. So we have this piece is what we're interested in. The total width is 15, and so we need to take 15 and take away 2x. And then the height, well, if we fold up the piece we're folding up, the height is the length of x, and so that is the height. And so we can just multiply out this quadratic, and we will get 360 minus 78x plus 4x squared. And then we have this x on the outside, which we can multiply in, and we can just rearrange the formula. So we'll get the volume equal to 4x cubed minus 78x squared plus 360x as required. So here we have an equation that describes the volume of this box as we change the value for x, and it's modeled after a cubic equation. So logically we can work out that in our cubic equation, when x is equal to 0, the volume should be equal to 0. So what I have here is I have the graph that we've just calculated the equation for, right? And what you can see is I have the volume on the vertical axis, and I have the x value on the horizontal axis. And as we change that value for x, you can see what the volume is doing, right? So as I increase the value for x, I'm making the height of that box slightly higher, and so the volumes be getting bigger and bigger and bigger and bigger until it gets to a certain point. And then at a certain point, we make X so big that even though the height is getting bigger, the width and the length are getting so small that the volume now starts getting less and less and less until I get to a point, well, logically I can work out that this is the point where I take away so much of X that I have no width left, right? Because I had a width of 15. If I take away 7.5, well, I'll have nothing left to calculate the volume with. And so I get back to 0. And then this part here represents negative area, which we don't consider because that's not existent. Right, so the only part of the graph that we're actually interested in is this first half. And the thing we would like to calculate, which we would not normally have a graph to do, is we'd like to calculate this point over here. Because the graph shows that this is the maximum volume that this box can be as I change X. And I'd like to find that, and I'd like to prove that that is the maximum value rather than the minimum value, which is down over here, which is an area or a volume that doesn't exist. So there's our equation. And the next part of the question is leading us onto that. They're saying find the stationary value for volume. So what is this stationary value? And we'd like the value of X for which this occurs. Now we actually need to find the X value first before we can find the Y value. So a stationary value is a turning point, right? A turning point and a stationary value are when the derivative, the gradient, is equal to 0. And we can see that on our graph. At this point here, the gradient is 0. So if I want to calculate that, I need to find the gradient equation. So we will just differentiate the whole equation with respect to X. And then I'll get an equation for dV on dx. Okay, so it won't be dy on dx because I don't have y, I have volume. So dv on dx is equal to, and just using the power rule, I will get 12x squared minus 156x plus 360. And so I can state for stationary points dv on dx, the gradient function, should be equal to 0, right? Because the gradient is 0 when I have a stationary point. So we'll just solve the equation, 12x squared minus 156x plus 360 equal to 0. So I'll start off by checking if everything is divisible by 12. And if it is, I'll just divide through by 12 to simplify. So I'm going to get x squared minus 13x plus 30 equal to 0. And then I'll just factorize. So I'm going to get x minus, looks like 10, x minus 3 equal to 0. Now remember, x is a length, so it can't be negative. So we get x equal to 10 or x equal to 3 as my two solutions. So both my solutions look like they can work. So what we need to do is go back to the original question and have a look at it and consider what is going to happen, whether if these both are going to work. So x equal to 3 will work for both the width and the length, but x equal to 10 will not work in this direction here because I can't take away 10 from both sides and go in, because then I'll be having negative length. All right, so x equal to 10 cannot be a solution. So we're only going to consider the x equal to 3 as one of our solutions. So we have our solution, x equal to 3, and they asked us to calculate the stationary volume. So we can't put 3 back into the gradient equation. That's not going to work. We need to put 3 back into the original equation because that gives us volume. So we went volume when x is equal to 3, we'll just go 4 times 3 cubed minus 78 times 3 squared plus 360 times 3. And we'll stick it into the calculator, and that's going to give us 486. Right, and this would be centimeters cubed because we were given centimeters. So we have a stationary volume of 486 when x is equal to 3. Now, the final part of the question asked us to determine the nature of the stationary point. Okay, we've got the stationary point, but is it the maximum, all right? Is it the maximum? Now, we know from the graph already that it is, but we won't always be presented with a graph, and we might not have graphing software, so we want to prove it algebraically. So to prove that a point is a maximum, we can either use a point before it and a point after, or alternatively, we can just consider what is the second derivative. So we're going to differentiate the derivative with respect to x, and we're going to get d squared v on dx squared. Okay, so I'll use the power rule again, and you're going to get 24x minus 156, not x squared, sorry. So what I need to do is I need to put my x coordinate into this function. So I want to know what the second derivative is here. So when x is equal to 3, let's see what d squared v on dx squared is equal to. So it's 24 times 3 squared minus 156, which is equal to minus 84. Now, I don't care about the minus 84 part. I only care about the fact that it's negative, okay? So what we need to remember is that when d squared v, so the second derivative, is less than 0, then we have a maximum point. And so this stationary volume of 486 centimeters cubed at x equal to 3 is a maximum. And so that is the maximum volume that can be created as we change x. Okay, in our next example, we are given a piece of wire that has a fixed length. It's bent into a specific shape, and we can vary what the length of x and the length of y are equal to. In other words, we can change the radius also of the circle by varying x, and so we could create all kinds of different shapes just by changing what these two lengths are. So we could make x smaller, and we could make, therefore, y would have to get longer, right? Because remember, there have to be a fixed length of 2 meters. So we could have a longer shape that curves back around. We could have many different types of shapes. And generally what's happening here is the question is leading us from one point to the other, right? And this question is actually quite nice because it's helping us along. It's helping us determine what the overall goal here is, to find what the maximum possible area is that we could make by changing x and y and creating different shapes out of this 2 meter long piece of wire, right? So in this question, they're leading us towards this goal, but sometimes, especially in exam questions, you need to intuitively follow this process by yourself. So generally, the first thing that's going to happen is we need to eliminate variables if we have multiple variables. We can't differentiate something. For instance, here we have the end area equation, and it has to be in terms of 2 variables. One will be the subject, and one will be the thing that's changing. We can't have 2 variables in this equation because then we can't differentiate it. So we need to, if we're not led in this way, we need to think in this way. So it's actually quite easy to think about the shape. Since the overall length of the wire is fixed at 2 meters, that means that this length going around here cannot be more than 2 meters. And that length going around there is the perimeter, right? We can look at this shape and think, well, how can I calculate the perimeter? So I can think about all the pieces that make it up. I go from T to P, and then I go from P to Q, and then I go around this arc from Q to S, and then I go from S to T, and then I'm back where I started. And so what I need to think about in terms of the shape is how I can make that. So T to P is just X, right? It's one of the sides that can vary. And so is Q to P, and s to t. They're both y's. So we have two y's going there. Then I have half the circumference of a circle. Okay, so I have half of the circumference of the circle. So what is the circumference of the circle? Well, it's 2 pi times the radius. 2 pi times the radius. And the radius in this example is, well, this length here is at x. So that means half of this length must be half of x. So x over 2. And that would give me the total perimeter. So we were asked to give an expression of y in terms of x. So what that means is I need to rearrange this to give me a formula for y equals. Okay, so I have, at the moment, the perimeter, and the perimeter is 2 meters long. Okay, and that must be equal to x plus 2y. I can simplify this to plus pi x over 2. And just by rearranging things, I'll get 2y equal to 2 minus x minus 1/2 pi x. And then dividing through by 2, I'll get y equal to 1 minus 1/2 x minus 1/4 pi times x. So now I have an equation for y in terms of x. And that's good because we're going to need that to eliminate the variable y in our next equation. So question B says, show that the area is equal to this equation. So when you get asked to show, the idea is that you just need to arrive at the same equation, right? So you need to pretend that you haven't seen this equation and just come up with an equation for the area. So the area of this shape would be equal to the area of that rectangle. And we're going to add the area of half that circle. That will give us the area of the enclosed area. So the area of the rectangle is just x times y, base times height, or base times length, whatever. And the area of the circle is going to be half of a circle, and the circumference, or the area of a circle is pi r squared. Pi r squared. So pi times the radius squared. The radius is half of x squared. And so what we get is xy plus, this is going to become here x squared over 4, and it's going to multiply by that half. So we're going to get x squared over 8 pi. And we want the area equation to have only x's in it. And so what we're going to do is we're going to substitute this y out for what we already put in. Unfortunately, it's not very nice, but that's just what we have to do. So we're taking x and we're multiplying it into 1 plus 1/2 x plus 1/4 pi x, and then plus this x squared over 8 pi. So multiplying the x in, I get x plus 1/2 x squared plus 1/4 pi x squared plus 1/8 pi x squared. These two terms are the same, and so we can add their coefficients, and that's good. Except that this was a minus sign, so let's just quickly change that. And this was a minus sign, so let's just change that. All right, so that's naughty. Keep track of your negative signs. So I can simplify by adding these two together. So if I have an 8, then I subtract 1/4. Well, then I'm going to get minus an 8. And so I've arrived at what I wanted. So the area is equal to x minus 1/2 x squared minus 1/8 pi x squared, right? As required. Okay, part C says find dA over dx and d squared a. So that's asking you to find the derivative of this equation and the second derivative. So it's leading on to find the maximum area and then proving it using the second derivative. So we also need to remember we'll have to find what this stationary area is in a minute as well. So C, let's find dA on dx. So we're differentiating the area with respect to x. So we can just use the power rule. So x becomes 1. And then we're multiplying by the power, so this half is going to go away. So we'll get minus x. And then we're multiplying that 2 by the 8th, and we're getting minus a quarter pi x. So there's my derivative. And now I want my second derivative. And so again, using the power rule, so the 1 is going to go away. The minus x is going to just become minus 1. And the minus quarter pi x is just going to become minus a quarter pi. So just by its virtue, because the second derivative doesn't have a variable, if we look at these numbers, this second derivative is negative. And so that means that the stationary point in this equation is going to be a maximum, right? It cannot be anything else. All right, so part D says find the value of x for which we have the stationary value. So let's find that value. So for a stationary point, the derivative, which in this case is dA on dx, should be equal to 0. So let's make the derivative equal to 0. Okay, so that means that we get 1 minus x minus 1 quarter pi times x equal to 0. So I'm going to move the x's over and I'm going to multiply everything by 4 to get rid of that quarter. So I'm going to get 4x plus pi x equal to 4. And then I'm going to pull out the x and get 4 plus pi equal to 4. And so x is going to be equal to 4 over 4 plus pi. So that's the value that is where my stationary point is at. Now I'm going to leave it like that because that's easier to put into my calculator to calculate the value. Now this value, this needs to go back into our original formula. So this area formula that we proved earlier on. So we need to put that into the formula, okay? Now I'm going to spare the gory details because it's quite long. So area would be equal to x, which is 4 over 4 plus pi, minus 1/2 of 4 over 4 plus pi squared, minus 1/8 of pi times 4 over 4 plus pi squared. And so we could expand and we could simplify. We will see we have a common denominator. And once we've worked that out, we're going to get 2 over 4 plus pi. So that is our area at the stationary value. Now all we need to do is prove that it is a maximum, right? Now I've already shown that just by virtue of the second derivative not being a variate function, there's no variable in there, it's a constant function. It's a negative constant function, meaning that it is always less than 0. So we can say d squared a over dx is less than 0, and therefore we have a maximum point. So a nice question to show you how we would follow a certain procedure to try and identify a maximum value and how to prove that it was a maximum value.